Hey, Science 30s, and welcome to our third and final discussion related to topic 2.1 in the Chemistry and the Environment unit, organic compounds. So far, we've talked about aromatic compounds like benzene. We talked about naming and the difference between the alphaics, which would be alkanes, alkenes, and alkynes. Today, I want to introduce you to the first of four functional group hydrocarbons that we're going to be dealing with. These are specific groups that have specific side chains that are different than your standard carbon and hydrogen configurations. So first of all, what is a functional group? Well, again, a functional group is a specific side chain or group that is located on a hydrocarbon, and that gives that particular molecule a different designation other than just an alkene, an alkyne, or an alkyne, or an alkane, or aromatic. These functional groups will basically designate that molecule as a different type of molecule. There are four functional groups that you're going to need to be familiar with in this course. We're going to deal with only one today. The next video is going to be discussing the other three. But today we're going to be discussing the first one, which are halogenated hydrocarbons. We're then eventually going to be discussing alcohols, carboxylic acids, and esters as well. So for today, and remember, all of this material, all of the information about these functional groups, again, page 9 of your data booklet for Science 30, it's all there, what the generic formula or designation of these functional groups are. It's all located on that page number 9 for you. So let's discuss what halogenated hydrocarbons are. Well, they're essentially hydrocarbons that have a halogen attached to them. And if you remember from your discussions in chemistry or in Science 10 or even back to Science 9, we discussed, when you discussed the periodic table, the second last column in the periodic table, right before the end where you have your noble gases, those are your halogens that they form ions that have a charge of -1. These would include such elements as fluorine, chlorine, bromine, and iodine. These are the four main halogens that are going to basically be found in these halogenated hydrocarbons. And basically, they have a general formula. They're indicated by a general formula by Q. So if you see it on your data sheet, it's going to give you R-Q. The R is going to represent the main chain hydrocarbon, either the alkane, the alkene, or the alkyne. And the Q is a designate to basically indicate that there is one or more halogens that are attached, as opposed to having hydrogens attached to the carbons as side chains. And I'll give you some examples. There's a couple written on the board already, but I'll give you some examples here to kind of figure out how you do it. There is a rule when you're dealing with the halogens. If you have these halogens present, you have to use prefixes to indicate these halogens. So if you have a bromine atom, you're going to use a bromo. If you have a chlorine atom, you're going to use the prefix chloro. If you've got a fluorine atom, you're going to use the prefix fluoro. And if you've got iodine, you're going to use the prefix iodo. So those are the four prefixes that you're going to need to be familiar with when naming these halogenated hydrocarbons. So let's take a look at one. We've got actually a couple up here on the board. We've got this one here that has a single carbon in the chain. So we know that that is some form of, it's methane. If this was simply hydrogens around it, we would label this as methane. But we don't just have hydrogens anymore. We've actually got 3 chlorines attached in places where we would expect to see the 3 hydrogens in a methane molecule. So how do we name this? Well, again, if you look on the notes here, and again, if you're following along watching me, basically, you've got to indicate that there are, in fact, 3 chlorine atoms attached to this methane chain. And it is a methane chain. We can still call it methane because we know it's methane. We know that it's essentially an alkane. So the methane is going to stay there. That's fine. We can still call it methane. But we have to indicate that this methane is not standard methane like CH4. This methane has 3 chlorine atoms attached to it. So we have to indicate this by writing down the fact that there is chloro. So the chloro would be the prefix for chlorine. So we're going to call this chloromethane. But we also have to indicate if there's more than one side chain. Back to alkenes, alkanes, and alkynes. If we had more than one methyl side chain or an ethyl side chain, anytime we had a side chain, you had to indicate with the prefix how many there were. If there was one, you wouldn't indicate it, but if there was two, it'd be di, three would be tri, four would be tetra, five penta, et cetera, et cetera. Well, these functional groups essentially are side chains. We have to classify them as side chains. So we have to indicate that there isn't, if I just see chloromethane, that would, to me, would only indicate that there's one chlorine atom, but there are more than one, there's three. So we're gonna call this atom, or this molecule, pardon me, we're gonna call it trichloromethane. That's the name of it. Trichloromethane. It's methane that has three chlorine atoms attached to it. It has another more common name you might know of it. It's called chloroform, which is used to knock people out. You put it in a rag, you breathe in that chloroform, and you knock someone out. So you might have heard of chloroform. That's chloroform right there. Let's take a look at a second one here. We've got a 2-carbon chain now. Here's my 2 carbons. And it's a single bond. So I've got ethane. I know that. So I know this is ethane. We can start with that. But my ethane has 3 chlorines attached over the 2 different carbons, and we've got 3 fluorines attached. So I know I'm going to have to use the prefixes chloro, and fluoro for sure, and I know that I've got 3 of each, so it's going to be probably trichloro, trifluoral, somewhere in there. But now I have to indicate which which carbon these halogens are attached to. So remember we had to mention, so like for example, if I had an alkane, I had 2 methyl groups on it, I would have to indicate, let's say it was butane, I'd have to indicate that it was 2,3-dimethylbutane, right? Which would be this one here. This is going back to our last. So if I had that with my alkane, here's a methyl group, here's a methyl group, there's my butane. I'm going to count them 1, 2, 3. So this would be a 2,3-dimethylbutane is what this would be. I have to indicate this now with my carbons and my halogen functional groups as well. Now the question is, which one is my first carbon and which one is my second carbon? In this case, I'm going to decide it based on alphabetical dominance. So I know that chlorine is alphabetically ahead of fluorine on the alphabet. I see more chlorines on this carbon, so because it's alphabetically first, this becomes carbon number 1, and that becomes carbon number 2. So in this case, when I name it, and then also my functional groups are going to be listed alphabetically, very much like what we did with our alkanes, alkenes, and alkynes. If I had an ethyl and a methyl side chain, the ethyl would always be listed before the methyl, because ethyl was alphabetically before methyl. So in this case, what I'm going to wind up with is I have to indicate that I've got 2 chlorines on the first carbon, 1 chlorine on the second carbon. So that's going to be indicated by a 1,1,2 trichloral. I'm not going to have enough room to write all this on the board. Oops. And then I'm going to also indicate, and that would be in between there because I ran out of room. So I've got 1,1,2 trichloral because I got 2 of them on the 1 and 1 of them on the 2 carbon. And now I've got 1 fluorine on the first carbon and 2 fluorines on the second carbon. So this one's going to be listed as 1,2,2 trifluoral. So this substance, it's a mouthful, it's going to be called 1,1,2 trichloral, 1,2,2 trifluoral ethane. A lot of words in that one, but that's how you name them. So it's really, you're using some of the conventions that we learned about with our aliphaix, but now you just have to know about the prefixes for the halogens. If you see a halogen, anytime you see a halogen on any kind of a substance in this unit, if you see a halogen, either iodine, bromine, fluorine, or chlorine, you pretty much are going to have to guess that it's probably going to be a halogenated hydrocarbon. Now, what are some of the uses of these halogenated hydrocarbons. Well, they've had a bit of a they were sort of, when they were first developed, and some of them were developed back in the 1920s or 1930s. One of them in particular has had a really sordid history and really did some damage after humans created it. This was a substance that didn't exist in nature. Humans made it. They created what were called chlorofluorocarbons, which I just gave you an example of on that last page there, that had the fluorine and the chlorine in it. These are better known as CFCs. Now, you've probably heard of CFCs. You definitely covered them in Science 9. They were synthetically created, and they were sort of considered to be magical chemicals because they didn't react. They were very, very non-reactive chemicals. They had really long staying power. They didn't want to react with anything. So they were very considered safe. They were very safe to use. You could breathe them in. They wouldn't react with your body tissues or anything like that because they just didn't want to break apart. So they were used as replacements in refrigerators for coolants in refrigerators like Freon. You may have heard of Freon. They were used in aerosol cans. They were used in fire extinguishers. And again, the miracle of them was they were non-reactive, which was great because they were considered safe. Back at the turn of the century, if you had an early refrigerator, the gases that were used in refrigerators early in the turn of the century were deadly. If you had a leak in your refrigerator, you could actually die from a poisonous leak from your refrigerator. That wasn't the case anymore with CFCs. So they were really touted as these miracle products, or chemicals. But in 1987, they were banned. They were banned outright in what were called the Montreal Accord, the Montreal Protocol that happened in 1987. Now, why was that? Well, the problem was ozone. CFCs would not react under normal circumstances. The only time that a CFC would actually eventually break down is if it got high into the atmosphere and it began reacting with UV radiation high up in the atmosphere, up in the stratosphere. At that point, the chlorine atoms would break away from these CFCs and then would try to react with whatever was available in the atmosphere around them. And in the upper atmosphere, we've got a layer of the gas ozone, O3. We've talked about ozone in the first half of this unit and its relationship to the development of smog at ground level. At ground level, ozone is not something that we want, but in the upper atmosphere, ozone plays an incredibly important role. It blocks out harmful UV radiation coming in from the sun that actually prevents, from rates of skin cancer and damage to organisms from these damaging ionizing versions of UV radiation, which are known as UVC rays. UVA, UVB are still, considered to be somewhat risky, but they're not as bad as what we would call these UVC rays. So what would happen is these chlorine atoms that were breaking off of the CFC molecules in the upper atmosphere were basically removing up to 100,000 ozone molecules by reacting with them. They would basically react with the ozone, break the ozone into oxygen and chlorine oxide, and then the chlorine would break away from that chlorine oxide to re-react. Those single oxygen atoms would then bond together to form oxygen. So it was replacing ozone with oxygen, which maybe sounds like a good thing, but in the upper atmosphere, we don't really need oxygen. We need that layer of ozone. And what was happening was, as these reactions were continuing in the upper atmosphere, they began to produce what were called ozone holes, or holes in the ozone layer, like you can see in this diagram here. In particular, one of the worst spots on the planet was over the Antarctic. There was scientists have discovered that the extremely cold temperatures above the Antarctic basically facilitated that reaction to move even quicker. So you were seeing more reactivity between the chlorine and the ozone in these really cold areas above the Antarctic. So that's why CFCs were banned in 1987. Now, the good news is the ozone layer now is on the mend. It's been now basically, these products have been banned for over 30 years now. And scientists are beginning to see that this ozone layer is beginning to heal itself, which is a great thing to see because Mother Nature will heal herself if you give her enough time. They suspect that the ozone hole that was created by the use of these CFCs in the 20th century could be repaired within our lifetime. They're saying by about 2050, 2055, we could see basically ozone levels back to normal in the upper stratosphere, and those ozone holes that were created are pretty much going to be a thing of the past. So a very kind of cool thing. But again, it took science and countries around the world to ban these products in order for this to happen. If they wouldn't have united about this, it could have been a very different story. If you want to see a little bit more about the ozone hole and how the ozone layer was affected by CFCs, take a look at that video, short little video to kind of recap what I've discussed there. But when you're discussing halogenated hydrocarbons, CFCs are sort of kind of the poster child that most people think about when they're thinking about halogenated hydrocarbons. Okay, there's a couple of other forms of halogenated hydrocarbons which I'll finish up with, and then that'll be the end of our discussion for today. There are three other types that you should be familiar with. There's DDT. We talked about DDT. I've talked about it with my Science 9s. I talk about it with my Bio 20s. It was a pesticide that was used in the 20th century, and it eventually became an issue. Now, I'm going to get back to this pesticide before I finish up my conversation here today, but there were some big ramifications with DDT, not with just the insects that it was trying to kill. It was other organisms higher up in the food chain that were being affected by this pesticide as well. Again, because halogenated hydrocarbons are considered to be very stable molecules. They don't break apart easily. They don't break apart, so you can't really destroy them. In that respect, they're very much like what I discussed in previous discussions, like with benzene. Benzene, we talked about with aromatics, very stable. They don't break down very easily. And if they're a problem for organisms, then how do you get rid of them? And in the case of DDT, it became a problem, which I'll get to here shortly. PCBs are another form of halogenated hydrocarbons. They stand for Polychlorinated Biphenyls. So they're almost like a combination between an aromatic and a halogenated hydrocarbon. They've got the ring structures, the phenyl rings, plus they've got some halogens attached to the phenyl ring. So they are classified as halogenated hydrocarbons, even though they're cyclical in design. They were produced for a wide range of uses up until the 1960s. They were used in electronics, coolants, engine oils, paints, caulking. They were used in a wide variety. Again, they don't break down, and that became the problem. As we began to use more and more of these products, there was really nowhere for these products to go or break down or disappear, and they do have toxic effects. They basically, chemicals have been discovered in humans. They can cause everything from a simple rash to lesions on the eyes, to irregular menstrual cycles, to cancer. There's all sorts of health issues that have been associated with these products, and when they get into your body, they have nowhere to go, and they just basically sit there because they can't break down. The last section, I guess, or the last example of halogenated hydrocarbons that you could see on a test or a quiz are known as dioxins or furans. And these are basically they arise from processes that use chlorine in them. The production of iron and steel uses chlorine. Burning of plastics and treated woods also releases dioxins and furans. That's why they say you should never burn treated wood if you've got, let's say, old fence posts that have been pressure treated. They shouldn't be burned in your fire pit because you are releasing these chemicals. Especially if you're close to the fire pit, you're going to inhale those vaporous products that are in the fire pit. So just things to be careful of. Recycling. A lot of recycled plastic that's going overseas to third world countries, they're not actually recycling. They're actually burning that plastic. And when they burn that plastic, you're going to get dioxins and furans as a released product. Again, they're very stable products. They do not break down. Like all halogenated hydrocarbons, they don't really break down. As well, you can find these products also in our lovely pastime for some people in tobacco smoke. You can also smoke this stuff when you're smoking cigarettes. You're also going to inhale and release dioxins and furans directly inside of your body. So another reason why these are a problem. Now, what do they do to your body? All sorts of things. Skin disorders, liver problems, immune and nervous system disorders, and certain types of cancer have all been related to dioxins and furans. Now, because all of these halogenated hydrocarbons, whether they're CFCs, whether they're PCBs, whether they're DDTs, whether they're dioxins or furans, they all are classified like benzene. They are classified as, where did I write it down here? I know I wrote it down. Here it is. I wrote it down right here. They're classified as POPs. They're persistent organic pollutants. They do not break down easily. Now, if this sounds familiar, it's because I've discussed this already in the first half of the unit. We discussed releases of heavy metals, mercury that gets released, aluminum that gets released out of the soil. These basically will enter food chains and will basically begin to magnify as they go up the food chain. These POPs will do the same thing. They will do what we call biomagnification. Again, that term comes up again right there. biomagnification or bioaccumulation, where these pollutants will actually get more concentrated the higher into a food chain you go, because the poison it gets brought in by a root system into a plant. The plant gets eaten by a herbivore. It gets more of the poison. The herbivore gets eaten by a first level carnivore. It gets even more of the poison. That first level carnivore gets eaten by a second level carnivore. It gets even more of the poison. Again, biomagnification of the poison. And this was a real issue. I just mentioned about DDT. DDT almost did in the peregrine falcons. It almost caused them to become extinct in parts of the world, extirpated in different parts of the world, because they were ingesting large amounts of this DDT. It wasn't killing the birds, but it was damaging their eggs. Their eggs became very weak, very brittle, very soft, and they would lay their eggs and their eggs would crack. So these birds couldn't actually reproduce. As soon as they banned DDT, and the reason they banned DDT, they did, back in the 1970s, is because they began to see increased levels of DDT in female breast milk. So it was actually when they began to realize that babies were actually ingesting this DDT through breast milk, that became the lightning rod to basically tell scientists and politicians, we got to stop using this stuff, DDT, because it doesn't break down, it doesn't break apart. It just, your body absorbs it and then doesn't know what to do with it. It just sort of stores it into a corner, and then it just reacts and has all sorts of nasty, sometimes unseen consequences inside of biological organisms. So that's basically why these substances are considered to be a real issue in the environment. Let's take a quick recap about halogenated hydrocarbons right up here. Take a look at that just to kind of wrap up everything that you need to know about halogenated hydrocarbons. Your homework for this section is going to be questions 1 to 3 and question 8 on page 245 to 252, and questions 2, 5, and 6 on page 262 of the Science 30 textbook. That is our final that's the trilogy of Organic Compounds 2.1. We're finally done it. 3 videos is all it took. We're going to be moving on next day to our discussion about alcohols, carboxylic acids, and esters. Until then, folks, thanks for tuning in, and we will see you next time.